Yes, good morning all the students. Let me share the screen first. Yeah, let's proceed with our sixth lecture under this module 2. In the previous class, we have focused on inductive bias in decision tree learning. What are the assumptions that are made in decision tree learning? And we understood that those assumptions are preferring shorter trees over longer trees, or preferring simpler trees over complex trees, and using information gain as the statistical measure in order to select these shorter trees, right? These two are the assumptions, or this is the inductive bias in decision tree learning. And also we understood the difference between restriction bias and preference bias. Now I have a small question for you. ID3 prefers restriction bias or preference bias? Can anybody answer? ID3 algorithm used for building decision trees from the training examples. It prefers a restriction bias or a preference bias. What is its strategy? Which one does it take as its inductive bias?
Preference bias.
Very good. It's preference bias. And what about finders and candidate elimination algorithms? What kind of bias is it? Preference or restriction bias? It's restriction bias. Why? Because you're trying to, the candidate elimination algorithm tries to minimize the version space in order to contain only hypotheses that are consistent with the training examples, right? So it is imposing a restriction on the hypothesis that should be stored in the hypothesis space. That is why we call it as restriction bias. Whereas in ID3 algorithm, in the hypothesis space, you have optimal solutions, but you select the solution which is small and simple, right? You're trying to prefer among the optimal solutions. That is why it is called as preference bias. And also we have seen Occam's razor theory, which indicates always the short hypothesis should be preferred over the long hypothesis, because it reduces the chances of coincidence and gives us the optimal solution, right? Say if we have less number of solutions, chances of coincidence also will be less in that. But if you have more number of solutions with long hypothesis, large number of hypotheses, in that case, chances of coincidence may be more, which may not generalize to the unseen data properly, which may not make good predictions, which may not make accurate predictions. That is why Occam's razor theory always says that go for shorter hypothesis, go for simple solutions when compared to larger solutions, right? So these topics are very clear to you now. Let's proceed with what are the issues in decision tree learning. This is very lengthy topic. Why? Because you need to understand very clearly about the concept of overfitting and underfitting. Not only with decision tree learning, but with many other machine learning models, this overfitting and underfitting problem occurs. By seeing overfitting, you should not be happy that your machine learning model is performing very well. You should also see the performance of the machine learning model with the test set also. Only if it is performing well with the test set also, then we say that your model is generalizable. Your model can predict well with unseen data. That is why there is a trap that may be caused due to this overfitting and underfitting, that you have to understand very clearly in order to take some good decisions when you become a machine learning expert, right? Now, initially, all these topics will seem to be too much mathematical or too much boring to you. But once that interest is triggered in your mind, you will feel to learn more and more about this machine learning concepts. So keep focused, stay focused. Okay, if you do that, if you start understanding, you will feel it more interesting to learn more and more. Okay, that is why I want you to concentrate in the class, right? Now, what are the issues in decision tree learning? Before going to discuss about these issues, let us see what are the practical issues in decision tree learning first. Okay, nominally, let us just list out all the practical issues so that we'll discuss about them in detail. So what are the practical issues in decision tree learning? Determining how deeply to grow the decision tree. You may not exactly know when to stop the construction of the decision tree. Now we are using information gain as statistical measure. Many such measures may be available. In such case, when to exactly stop to grow the decision tree? Say you're taking information gain as the statistical measure, and you have partitioned now by taking a split point here. Say outlook value. Now you're taking humidity here. After using humidity as the split point, you're dividing the training examples, and here you have training examples, 4 positive examples and 2 negative examples. Now, can you stop here, or you want to proceed further in order to get more better classification, more pure classification, such that in all these 2 negative examples, take again another node here, so that all will be classified as negative examples and no more will be classified as positive examples. And in this, all will be classified as positive examples, and no training examples will be classified as negative examples. You are trying to select such a attribute here as the split point. What is happening here? You can actually stop here because you are almost near pure classification, 4 and 2. But still you can extend the tree also in order to get completely pure classification, so that you have only all positive examples and no negative examples, only all negative examples and no positive examples. In order to get in that way, you can keep on building the decision tree. You can keep on expanding your decision tree in order to fit your training examples, right? So what is the end point? What is the termination condition where you have to stop building this decision tree? That is one practical issue. Okay, then how handling continuous attributes. Say your decision tree works well with categorical attributes because your final outcome will be yes or no, 1 or 0, fraudulent or not fraudulent, genuine or not genuine. Like that, you have categorical outcomes that can be given by this decision tree. But if you have continuous attributes, how to handle that continuous attributes, that also we are going to see under this discussion about issues in decision tree learning. Now, choosing an appropriate attribute selection measure. Now, how to select the appropriate attribute selection measure? Whether I should select information gain, or whether I should select entropy, or whether I should select entropy within information gain, or what other measures we should select in order to choose the appropriate attribute that can be taken as the split point in the decision tree. Split point means you know very well now, right? The root node of any tree or subtree is called as split point. Okay, now how to choose that measure? Like information gain, many other measures may be available. How to choose the appropriate measure? That is one more issue. That is one more practical issue. Now, handling training data with missing attribute values. If the training data doesn't have some attribute values, say the weight of a person is given as 0, or the phone number of a person is given as 0, the value is missing. In that case, how to categorize that particular training example? If the split point taken is weight, and weight of that person is not known, then how to put him in this S category or in no category, or in greater than 50 kgs category or lesser than 50 kgs category? How can you handle that data? That is another issue. And handling attributes with differing costs. If the attributes have different weightages, okay, then how to handle that particular attribute. And improving computational efficiency. While you're expanding your tree, while the decision tree is growing complex and complex, more complex and more complex, in that case, the efficiency of the model will reduce. Why? Because it will take more time to predict something, going through all the branches and all the levels of decision tree. In that case, how to improve the computational efficiency? By reducing the complexity of the decision tree. That is another issue. Now, ID3 has been extended to address most of these issues. Original ID3 algorithm, the basic ID3 algorithm doesn't address any of these issues, but as that has been extended in order to address most of these issues that I have listed here, with the resulting system renamed as C4.5 or classification 4.5. The new algorithm, extended form of ID3 algorithm, is known as C4.5. Right? Now let us see how all these issues have to be understood and how to overcome those traps. Okay? Now let me list out the issues we are going to discuss here in today's and next session also. That is avoiding overfitting the data, incorporating continuous value attributes when you're using decision trees as the learning model, and alternative measures for selecting the attributes, and handling training examples with missing attribute values. If at all attribute values are missing, in that case, how the classification have to be done, and handling attributes with differing costs. If the attributes have differing costs, how to handle them. Okay, that these issues we are going to understand in depth so that we can avoid those issues when we are trying to make our machine learn this decision tree model. Now, how to avoid overfitting the data? The ID3 algorithm grows each branch of the tree just deeply enough to perfectly classify the training examples, right? So when you take ID3 algorithm, it starts with the root node. A condition is checked. If the condition is yes, do something, or no, do something. Means to classify the training examples. Now another attribute is checked here. Now based on that attribute values, you further classify the training examples. Now this ID3 algorithm, what it actually does is it grows each branch of the tree just deeply enough to perfectly classify the training examples, right? So by the end of building of this decision tree, you get a optimal decision tree which will answer all your training examples, right? Because it has learned from those training examples. Now, it may lead to difficulties when there is noise in the data, or when the number of training examples is too small to produce a representative sample of the true target function. When very less number of training examples are given, this decision tree can't be optimally built because it can't learn sufficiently from less number of training examples. And sometimes when there is noise in the data, what will happen? Say there is an outlier. Age, instead of 20, it is given as 120. It is wrongly noted as 120. Now, decision tree algorithm will try to fit that condition of age also. In that case, it has to extend one more branch in order to perform a pure classification for that outlier. Means the complexity of the decision tree is increasing for the sake of noisy data, for the sake of outliers, which is not acceptable. You understood what I'm talking about? When the data is having some outliers, means when the data is having noisy values, noisy data, when the training examples are having noisy data, then in order to fit those outliers, the tree will be extended longer and longer, which will result in complex decision trees. And it will answer every possible unseen data correctly, and sometimes it may not be able to cover some conditions. I'll show you how it will happen. In the previous chapter also we have seen, if one training example is one unseen example is given, in that case, though its value is S, it may predict as no, because this combination of attributes, it is checking for every possible alternative. That is why it is okay with any of the values. So whenever it has to be classified as no, it actually classifies it as S, which is wrong classification. Correct? In that case, this will result in overfitting of the data. It can't generalize well with unseen data. It can't predict correctly with unseen data. Got it? That is why the difficulties start arising when there is noise in the data and when there are too less number of training examples. The decision tree may not be able to generalize well with unseen data. Okay. Now, in either of these cases, this simple algorithm, ID3 algorithm, can produce trees that overfit the training examples. You understand this concept, it will look very exciting for you. Whenever you come across this overfitting, when you're working with real-time data, you will understand it is exactly not good performance of the data, model. It is overfitting of the model. If you think overfitting has good performance of the model, you come out with bad models which can't generalize well to the unseen data. If it is not able to predict properly with unseen data, what is the use of developing a machine learning model? Do you want to become such expert in machine learning who will give wrong results? No, right? He should be very authentic. Machine learning expert should be very authentic in developing the models. He should not convey wrong results through his models. Remember this. Okay? Now let us understand what exactly is overfitting and how to avoid them. How to check for them and how to check for that particular phenomena and how to avoid it. Right? Now we say, let us understand it somewhat formally. Okay, then again we'll come back to understand it with an example. Now we say that a hypothesis overfits the training examples. When we say it overfits, if some other hypothesis, if at all there exists another decision tree, in this case, what is hypothesis? Decision tree. In finder's algorithm and candidate elimination algorithm, what is the hypothesis? It is a statement. But in decision tree learning, what is the hypothesis? It is a decision tree, optimal decision tree, right? Now we say that the hypothesis overfits the training examples. If some other hypothesis, say another decision tree exists that fits the training examples less well, actually performs better over the entire distribution of instances. You have entire distribution of instances. Instances means training examples. Training example 1, training example 2, up to training example 100, say. You have 100 training examples. Now, whenever you're testing your model, you have to actually divide it into two parts, training set and test set. Normally 30% means one third of the one third of the data set is taken as test set and two-thirds of the data set is taken as training set. If you have 100 training examples in the data, 100 data points in the training in the data set, you take 66 or 67 for training and 33 for testing. Okay, that is how you need to divide your data set. Now, train your model on the training data and see how well it performs on the test data, because this test data is not seen by your machine. So give your test data to the machine, hide the labels, hide the outcomes, and see what are the predictions, tally with your outcomes, original outcomes, and see what is the deviation. That will help you to calculate the accuracy of your model. Got it? That will help you to measure the accuracy of your model. Now in your test set, you have 33 data points. In that you have 33 labels, right? Hide these labels and give only the attribute values to your model, which is already trained on your training set. Now your model will predict the labels of these attributes. Now tally those labels with these hidden labels. What is the error in prediction? Say among these 33, 20 of the labels are predicted correctly. Only 10 of them are not predicted correctly. In that case, we measure the accuracy as 20 by 30 into 100. Right? That is how the accuracy of any machine learning model can be measured. Now you understood what is training set and test set, right? Now let us go back. It will be more clear for you now. We say that a hypothesis overfits the training examples if some other hypothesis, say another decision tree exists that fits the training examples less well, actually performs better over the entire distribution of instances, means better with the test set. If it is performing better with the test set, then it is said not to overfit. If it is not performing better with the test set but performing better with the training set, then it is said to overfit. Okay, this concept keep in mind. It will be made more clear further. Okay, now let us see the definition first. Given a hypothesis space H, understand carefully, a hypothesis H belongs to H is said to overfit the training data if there exists some alternative hypothesis H dash belongs to H such that H has smaller error than H dash over the training examples, okay, but H dash has a smaller error than H over the entire distribution of instances. Means H dash has a smaller error than H over the test set, they actually mean. Unseen data, which is drawn from the same data set, right? So it will also have the same distribution as training set. That is why they are telling entire distribution of instances. Understand carefully. When I take the data set, all the data points in the data set are derived from the same distribution. All the instances will have the same distribution. Now, if a model is performing well on training set, it has to perform well on the test set also. If it is performing well on the training set and not performing well on the test set, then we say it is overfitting. If at all there is another model which is performing well on, not too good on training set, but performs good on test set also, then we say that the previous hypothesis is overfitting and our current hypothesis is performing good. Right? In this case, H dash is the simpler hypothesis, simpler decision tree. It is fitting the decision tree and the training examples moderately, and it is performing well with the test set also. Then we say it is not overfitting. But there is a hypothesis H belongs to H, which perfectly fits the training set, but not performing well with the test set. Then we say H is overfitting. H dash is not overfitting. H is overfitting. Got it? Now let me read the definition once again. Given a hypothesis space H, a hypothesis H belongs to a hypothesis space is said to overfit the training data. When it is said to overfit the training data, if there exists some alternative hypothesis H dash belongs to the hypothesis space such that H has smaller error than H dash on the training examples, but H dash is performing well. H dash has a smaller error than H over the entire distribution of instances. Means over the unseen data, over the test data, H dash is performing better than H. Then we say H dash is good fit and H is overfit to the data set that is given. Right? This is definition of overfitting. H dash is simpler hypothesis. H is complex hypothesis. Because it is complex, it covers each and every training set. That is why it is overfitting the data. It is learning too much from the data. But H dash is optimally fitting the decision tree. Simple and very short tree. It is generalizing well with the test data also. That is why we say H dash is not overfitting. H is overfitting. Okay. Now after the class, read the definitions once. You will clearly understand. Keep in mind what is training set, what is test set, and understand when a hypothesis performs too good with training set and not good with test set, it is overfitting. If a hypothesis H dash is performing moderately with training data as well as performing good with test data, then we say it is a good fit of the data set that is given. Got it? Now see this, it is figuratively represented. The ID3 algorithm is applied, say, to the task of learning which medical patients have a form of diabetes. Okay, so it is trying to make some prediction about diabetes patients. In this case, listen carefully. This x-axis represents the number of nodes in the tree, and the y-axis represents the accuracy. Now, as ID3 algorithm builds the decision tree with 10 nodes, 20 nodes, as the number of nodes in the decision tree increases, even the training and the test set performance increased. But did you notice here, at a crucial point around 25 nodes, the training set performance after 25 nodes, you keep on adding 100 nodes to the decision tree, training set accuracy increases. But did you see a drop in the test set accuracy? Around 25 nodes, here the test set accuracy started dropping. Means the generalization capacity of your model is deteriorating. It started coming down because your model is learning too much by including large number of nodes into the decision tree. It is answering for every possible combination. In such case, when it is given with an unseen combination and that is not seen by the model that it is trained on, it will give wrong predictions. That is why the test accuracy started coming down. This is how you need to understand about overfitting. If your training data is giving too good accuracy and your test data accuracy is falling, then we say the model is overfitting. When it started overfitting? Around 25 nodes. So you have to be cautious. You have to be careful around this range of 25 nodes and stop fitting your decision tree. Stop expanding your decision tree. You have to take a decision somewhere around 20 to 25 nodes to stop the construction further of this decision tree so that your model will not overfit and it would generalize well with the unseen data, that is the test data, so that both of their accuracy will be correct and good enough. I don't say more or less, good enough. Okay. Now that is what is explained here. The horizontal axis of this plot indicates the total number of nodes in the decision tree as the tree is being constructed. And the vertical axis indicates the accuracy of predictions made by the tree. Now the solid line shows the accuracy of the decision tree over the training examples. This one, this is the solid line, which shows accuracy of the training examples. And this dotted line shows the accuracy of test examples. Now, predictably, the accuracy of the tree over the training examples increases monotonically, slowly, gradually it is increasing as the tree is grown, as the levels in the tree keeps expanding, the training data accuracy increases, but the accuracy measured over the independent test examples, these are hidden examples which are not shown to the model, and we ask the model to predict the outcome label of this unseen data, that performance, that prediction started coming down. First, they increased up to some extent. After that, they couldn't generalize well. They couldn't predict well. They are dropping down. The accuracy is dropping down. Why? Because the model is answering for every possible alternative combination and all disjunctions, I mean. And it is not trying to understand a particular combination of attributes when some unseen data is given. So it wouldn't be able to generalize well on the new data or unseen data. Now, one way this can occur is when the training examples contain random errors or noise, right? Say in your previous case, your decision tree has two levels, but if there is some noise in the data, there are too many labels under the attributes. There are too many categories under the attributes, and there are outliers under the attribute values. In that case, the tree has to be grown in order to give better classification and or pure classification. What happens here? The complexity in the tree is increasing in order to accommodate for even the noise in the data, even for outliers in the data. Means every possible combination it is considering. Then do we call it as optimal decision tree? We call it as decision tree, that's all. But we doesn't call it as optimal decision tree. To illustrate, let me give you an example. Consider the effect of adding the following positive training example incorrectly labeled as negative to the training example set that we have taken in the beginning of this chapter. 14 days data is given and labels whether tennis is played on those days given the climatic conditions, given the weather conditions, right? Now to that data set, let us assume 15th data point is added. Outlook sunny, temperature hot, humidity normal, wind strong, and the label as no. Okay, it is incorrectly labeled as no. Actually, its label is S. Means this is noise in the data. You can treat this as noise in the data. Now what will happen? Your decision tree will further be extended. Actually, your decision tree for these 14 training examples, it has two levels. But in order to accommodate this noisy data point, it will extend the decision tree further to 3 levels or sometimes 4 levels. What is happening here? Your tree is growing complex. It is accommodating every possible combination. Now, when a new data point is given with combination near to it, it will predict wrongly, right? It can't generalize well. The addition of this incorrect example will now cause ID3 to construct a more complex tree. That is what I said. Now the result is that ID3 will output a decision tree H, now a new decision tree, complex decision tree that is more complex than the original tree H dash. Now what is happening? H will not generalize well with the new data, whereas your old tree, simple tree H dash, will generalize well with the new data. That is why we say H to be overfitting. Now I think if you go back to your definition, you'll understand it better. Why H is said to be overfitting, whereas H dash is assumed to be a good fit. Got it? This is explained better. H will fit the collection of training examples perfectly. Yes, it may suit perfectly. Even the noisy data it is accommodating. Whereas simpler H dash, your original decision tree, will not fit your example because new example is given with noisy data. Your old decision tree will not fit. It is not consistent with the new training example. And we expect H to outperform H dash over subsequent data drawn from the same instance distribution. Now listen carefully. H dash is your simple tree. H is your complex tree. Listen carefully. H is consistent with all your training examples. Your old simple tree H dash is not consistent with the 15th example given in the previous slide. Now, what do you actually expect here? Because H is consistent with all the training examples, it should generalize well with unseen data. Because H dash is not consistent with the new training example, we may think that it may not generalize well with the unseen data. But opposite happens. H may not be able to generalize well with unseen data, but H dash will generalize well with your unseen data. Why? Because it is not compromising with every alternative like your complex hypothesis H. It is very strict in its considerations. So it makes better predictions when compared to H. Did you understand? Now, overfitting, how it happens? It is due to random noise in the training examples that we understood. And sometimes when the training data is noise free, when there is no noise in the training data, still when small number of examples are associated with leaf nodes, means when there are less number of training examples given for the training, in that case also overfitting may happen. Okay? Say you have a decision tree like this. Now you have one positive example and one negative example. Still your entropy is very high here, right? It is as much as 1. When entropy is high, information gain is less. But do you stop here? If you expand further in order to gain pure classification, you tend to overfit. Or when there is no sufficient training example, you have to stop here. You can't expand the tree. In that case, what happens? There are small number of examples that are associated with the leaf nodes. And it can't expand the tree further because no sufficient training examples are given to further classify them. So overfitting happens in 2 instances. One is when there is random noise in the training examples, and one is when there are less number of training examples at the leaf node or insufficient training examples provided to the model to learn from. Okay? Now there are several approaches to avoiding overfitting in decision tree learning. Yes, there is some problem. Obviously, solution also will be there. Okay, that is why when you get stuck with some problems, you should not worry. Solution will be already available. Only thing is you have to uncover that solution. In your life also, if you come across some problems, do not worry. Solution is already there for that. Only thing is you have to work hard, uncover that solution. You can find out the solution for that problem, right? So there are several approaches to avoiding this overfitting in decision tree learning. These can be grouped into 2 classes. What are the solutions available? They are categorized into 2 classes. They are categorized into 2 parts. Let us see which would be more efficient, which would be more successful, which would be more practical enough to implement. Okay? Approaches that stop growing the tree earlier. Understand this? Approaches that stop growing the tree earlier. When it has to be stopped, it has to be stopped. In your parents will be saying, right? Some things should be done in life when they have to be done. Right time has to be noticed. Approaches that stop growing the tree earlier, when it is the right time to stop growing the tree, before it reaches the point where it perfectly classifies the training data. Let it not overgrow and overfit the training data. Find out a point where the growth of the tree has to be stopped in time so that your model will not overfit with the data. The number of nodes in the decision tree have to be decided properly, where the growth of the tree has to be terminated so that it does not overfit the training data. And approaches, what is the second part? Approaches that allow the tree to overfit the data. First, it will let the tree overfit the data, then start pruning it, and then post prune the tree. When some tree or a bush is overgrown, what do? You try to prune it, right? You take a cutter, plant cutter, and you try to prune the tree. Same thing. If the tree is overfitting, your training examples, let it overfit first. Then try to cut the nodes which is not giving good performance. That is called as post pruning method, post pruning of the tree. Okay, we have another 10 minutes. Let me complete good enough content. Now, what is the key question? What criterion is to be used to determine the correct final tree size? Okay, I said you have to stop the growth of the tree at the right time. But what is that right time? What criterion has to be used in order to determine the correct final tree size? How do you indicate? How do you notice that? Use a separate set of examples, training examples, test examples, distinct from the training examples to evaluate the utility of post-pruning nodes from the tree. You can write this as test examples. Use a separate set of examples. We call it as test examples, distinct from the training examples, separate, split the data set to evaluate the utility of post-pruning nodes from the tree. The tree is grown, remove this node. Is the test set giving good performance than the previous one? Yes. Yes, then your decision of pruning that node is correct. Now select another node to be pruned. Removing this, is it giving best performance with your test set? If it is giving best performance, your decision of pruning that node is correct. If the test set is giving worst performance than before, then pruning this node is not correct decision. Keep it in the tree. Try with another node. That's all. That is how post pruning happens. When you divide the data set into training set and test set, train your model on the training set and let it build the decision tree. Now start cutting the nodes in the decision tree. Start pruning the nodes in the decision tree. How to prune, how to make a decision to remove a node from the decision tree? Check that model's accuracy with the test data points. If it is giving good accuracy than before, remove that node, prune that node. If it is not giving good accuracy than before, keep the node. Do not prune it. That is the decision criteria, right? Normally, as I said, 1/3 of the data set is taken for testing, and 2/3 of the data set is kept for training. But if you want more training to be made for the model, in that case, 80% also can be kept for training and only 20% can be retained for testing, right? It depends on the context. When you become expert in this machine learning, you will understand what should be the training and the test split. Okay. Now use all the available data for training. Now, 2/3 of the data is available for training, right? Use all the available data for training, but apply a statistical test to estimate whether expanding a particular node is likely to produce an improvement beyond the training set. Okay, means you have to check some measure whether you have to retain that particular node in the expansion or remove it. Now use an explicit measure of the complexity for encoding the training examples and the decision tree, halting growth of the tree when this encoding size is minimized. Also you can take some other measures like encoding measures. When that encoding size is minimized, that you can in that case you can stop the growth of the decision tree. Okay, so these are all the measures, these are all the criterion which you can follow in order to prune the overgrown trees, prune the overfitting trees, right? Normally we go with this first criterion only. It is simple as well as efficient. Okay, now I think we better stop here. Why? Because this is a continuous topic. If broken in the middle, you may not understand. Now, there are two types: reduced error pruning and rule post pruning. There are two methods in order to avoid this overfitting of data. Let us see that in the next class. Let us move on slowly, because this understanding will make you develop good machine learning models. That is why these concepts, though it seems to be theory, these concepts are very, very important. And in your textbook, it is very lengthy. Those who are interested, you can go through the textbook concept. But what notes I have given in this presentation, this is enough for preparing for the exam. Okay, I have sufficiently covered. But who want to gain expertise in this particular topic, you can refer to the textbook also. That is actually what is anticipated from students. That is what is expected from students. Okay, let us stop here. Though we are stopping in the middle of this issue being discussed, we have to stop here because there are two concepts that have to be discussed elaborately in your next session, right? Any doubts still here, students? Did you mark your attendance, all of you? Very less number of students are there in the class. Okay, let's meet in the next class to proceed with the discussion.